Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Calculus series and concerns what is differentiation. This guide introduces the concept of differentiation and the language associated with it. It makes the connection between the derivative of a function, the rate of change of a physical quantity, and the gradient of the graph of a function. Introduction. The study of how one quantity, such as distance travelled by a car, is affected by another quantity, such as time, involves the use of differentiation. If the car is travelling at a steady speed on a motorway, then the problem is straightforward. However, if the car is stopping and starting in a city, then the exact distance it has travelled at any time can only be calculated by measuring its position at many small time intervals. The branch of mathematics concerned with infinitesimally small changes is called calculus. Calculus has two branches, differentiation and integration, and the two subjects were independently unified by Sir Isaac Newton and Gottfried Leibniz in the 17th century. To find out how a variable, for example y, changes with respect to another variable, for example x, you need to differentiate it. The result is the derivative, which is written like this and is pronounced dy by dx. Differentiation can be thought of as the study of the rate of change of one variable with respect to another. How to describe these changes is crucial to the mathematical modelling of processes which occur in many disciplines. Subject: physics. Symbol: ds by dt. Description: velocity, which is the rate of change of distance s with respect to time t. Subject: chemistry. Symbol: dA by dt. Description: the rate of change of the concentration of chemical A with respect to time t. Subject: economics. Symbol: dq by dp. Description: the rate of change in demand Q for a good as the price of the good P changes. Subject: biology. Symbol: dp by df. Description: the rate of growth of a population P with respect to food availability F. In this guide you will learn how the rate of change or derivative of a function is the same as the gradient of the graph of the function. You will learn how to calculate gradients for straight lines and see how this can be generalized to approximate the gradients of curves. Most importantly, you will learn that the terms rate of change, dy by dx, gradient, f dash of x, and derivative are all equivalent. Before you attempt to understand what differentiation is, you should first be familiar with the relationship between a function and its graph. See the study guides, the straight line, functions, using functions, and sketching a graph. This guide is not about learning how to differentiate. You can find this out by reading the study guides, differentiating y equals ax to the n, differentiating basic functions, the chain rule, the product rule, and the quotient rule. Gradients of straight lines. You may be familiar with the road sign which gives the gradient of a slope as a ratio 1 to 5, for example. This means that for every 5 metres you go along, you go 1 metre up. Mathematically, the gradient of a straight line is the amount you go up divided by the amount you go along to the right, or, in other words, the change in x divided by the change in y. Gradient equals delta y divided by delta x. Here, and throughout mathematics and science, the capital Greek letter delta, this symbol, is used to indicate a change in a variable. So, delta y means the change in y, and delta x means the change in x. Then, in the road example, if delta x is the distance travelled along the road and delta y is the height you have climbed while going along this distance, then a 1 to 5 slope has a gradient of delta y over delta x equals 1 over 5, which equals a fifth. Another way of thinking about this is that the rate of change of the height of the slope with respect to horizontal distance is 1/5. You can apply this to find the gradients of graphs of functions. Example: what is the gradient of the graph y equals 4x? From the graph of y equals 4x, you can see that the line goes through the coordinates 0, 0 and 3, 12. So, between these points, the change in x is delta x equals 3 minus 0, which equals 3. And the change in y is delta y equals 12 minus 0, which equals 12. And so the gradient, or the rate of change of y as x changes, is delta y divided by delta x, which equals 12 divided by 3, which equals 4. You may have been able to see this straight away if you knew that the graphs of the form y equals mx represent straight lines which pass through the origin and have a gradient m. See the study guide, the straight line. The graph above shows y equals 4x, which is one of the form y equals mx with m equals 4, and so the gradient of the line is equal to 4. Whatever 2 points you choose, the gradient will be the same. For example, using the coordinates 1, 4 and 2, 8, the change in x is 1 and the change in y is 4. So the gradient is delta y over delta x equals 4 divided by 1, which equals 4. The gradient is the same everywhere along the line. This is what straight line means. Differentiation and gradients. Differentiating a function gives the gradient of that function. Another way of saying this is that the derivative of a function is the same as the gradient of the graph of that function. For functions of the form y equals mx described above, the gradient is always equal to m, and so the rate of change of y as x changes, or, in other words, the derivative of y with respect to x, is always equal to m. The notation for the derivative of a function y, which is differentiated with respect to x, is dy by dx. This comes from the notation used above to calculate the gradient of a line, where the delta sign has been replaced with a d. In both cases, the delta and the d represent a change. For a straight line, this is exactly the same as the formula for the gradient. For a straight line, y equals mx, the gradient is dy by dx equals m. So, in the example above, for y equals 4x, the gradient is dy by dx equals 4. Differentiating functions. If the number of rabbits in a field at time t is given by the function r of t, then you can call the rate of change of the population of rabbits with respect to time dr by dt. To start with, if there are very few rabbits, then the population increases slowly and the rate of change of the population is small, so that dr by dt is small to begin with. As the population of rabbits increases, as there are more and more rabbits breeding, the rate of increase in the rabbit population will also increase, so that dr by dt increases as time goes on. Furthermore, as rate of change means the same as gradient, the gradient of the graph of r against t is changing, and so the function is not a straight line but a curve. In general, functions f of x are more complicated than y equals mx and have graphs that are not straight lines but curves. This means that the gradient of these functions is not the same everywhere but is also changing with x. So, the gradient of a curve is another function of x which is written as this and said f prime of x, or sometimes f dash of x. For a curve y equals f of x, the gradient is another function, dy by dx equals f prime of x. Alternatively, the notation y prime of x is often used. In the rabbit example, the gradient or rate of change of the rabbit population is r prime of t. What is this function, f prime of x? There is no easy answer to this as it depends on what the original function f of x is. You will need to read the study guides recommended in the introduction to help you calculate f prime of x. For now, it is important to realise that the gradient of a function is another function, and so changes at different values of x. Example: what is the gradient of the function f of x equals x plus 1 all squared at x equals 0? For the straight line, the gradient was the same everywhere, but now, as x increases, the function's curve becomes steeper. In other words, the gradient f prime of x is also a function of x. In order to learn how to find this function, f prime of x, you can read the study guide, Differentiating y equals ax to the n. However, there is a way of approximating the gradient of the curve at a single point, x equals 0. This is a graph of y equals x plus 1 all squared. The table below shows the gradients delta y over delta x of the straight lines on the curve of the graph. When x is 4, y is 25, the change in y equals y minus 1, which is 24, the change in x equals 4, and so delta y over delta x equals 6. That is the gradient of this line. When x is equal to 3, y equals 16, the change in y is equal to 15, the change in x is equal to 3, and therefore delta y divided by delta x equals 5. That is this line. When x is equal to 2, y is equal to 9, delta y is equal to 8, delta x is equal to 2, so delta y divided by delta x equals 4. That is this line. When x is equal to 1, y is equal to 4, delta y is equal to 3, delta x is equal to 1, so delta x over delta y is equal to 3. That is this line. It can also be shown that when x is equal to 0.5, y is equal to 2.25, delta y is equal to 1.25, delta x is equal to 0.5, therefore delta y divided by delta x is equal to 2.5, and when x is equal to 0.25, y is equal to 1.5625, delta y is equal to 0.5625, delta x is equal to 0.25, therefore delta y divided by delta x is 2.25. It is not possible to calculate the gradient of the straight line when x is equal to 0, because this will give delta x equals 0, and dividing by 0 is never allowed. However, you can see from the graph that as x becomes smaller and smaller, each of the lines on the graph gives a better and better approximation to the gradient of the curve at x equals 0. Also, the table shows that as delta x gets closer to 0, the gradient, delta y divided by delta x, gets closer to 2. So it seems that a good approximation to the actual gradient at x equals 0 is 2. Differentiation from first principles. The example above illustrates the basic idea behind differentiation as described by Newton and Leibniz. This is, for any function, as delta x gets close to 0, the gradient of the straight lines get closer to the actual gradient of the function, so that as delta x approaches 0, the gradient, delta y divided by delta x, approaches dy by dx. Further guidance and information. If you have any further questions about calculus or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of calculus, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.